In this video, we will start with chapter 11, which is on the case of more than one choice variable. Just change that to more than one. Okay, more than one choice variable. Section 11.1 is the differential version of optimization conditions. This will be self-study. And section 11.2, we will start with the extreme values of a function of two choice variables. So before we had f of x is some function of x. Now we move to the case where our function z is determined by x and y. So z is a function of x and y. That means our derivative of z will be the partial derivative with regards to x plus the partial derivative with regards to y. Graphically, we move into 3D graphs. How do we find the extreme values? So first, our first order derivative condition. Before we had f of the derivative f prime of x must be equal to 0. Now we have the partial derivatives fx and fy must both be equal to 0. Our second order derivative conditions, we now have multiple conditions. So we have, so let's just first do what our second order derivatives will look like. So first we will have the partial derivative with regards to x of the function. We will have the partial derivative with regards to y of the function, dz dy, and we have a cross partial derivative or fxy. This is the derivative with regards to x of the partial derivative with regards to y, or fyx will be the partial derivative with regards to y of the derivative with regards to x. So how do we find the extrema? So first, our first order partial condition is that the partial derivatives must be equal to 0. The second order condition is the second order derivative smaller equal to 0 is a maximum if the second order condition with regards to x is smaller than 0 and the second order condition with regards to y is smaller than 0 and the product of fxx fyy must be larger than f squared of xy. Our second order condition for minimum is d squared z is larger equal to 0, then it's a minimum, and we get this if fxx is larger than 0 and fyy is larger than 0, also larger than 0, and fxx, fyy is larger than f squared xy. We have a third option, so if d to z is equal to 0, this is called a saddle point. And this can happen if fxx, fyy is smaller than f squared xy. So let's do an example just of the derivatives. So say we have the function z is a function of x and y, and it's equal to 3x squared y squared plus 4xy cubed plus 7. So let's find the partial first and second order derivatives. So first we have dz dx, or equal to f of x. This will be equal to 6xy squared. So in this case we consider y as a constant. So that would be 2 times 3x y squared plus 12, plus x times 4 is 4y cubed. Okay, then there must be 7y. Okay, so let's just make a note. Y kept constant. With regards to with regards to y, is equal to 2 times 3 is 6x squared y plus 12xy squared plus 7. Our second order conditions, before we go on to the second order conditions, x is kept constant. Our second order conditions, we take our first order derivative and we take the derivative of that with regards to x. So fxx will be equal to 6y squared. Fyy is equal to 6x squared plus 24xy. And our partial derivatives, xy, so we take y with regards to x is 12xy plus 12y squared. Fyx is taking x with regards to y, so that will be that function with regards to y, so that is 12xy plus 12y squared. So it's important to note that these are equal, so you can remember that fxy will always be equal to fyx. So you only need to calculate one. So let's do an example of the local maximum, maxima, minima, and saddle points. So say we have the function f(x,y) equal to x4 minus plus y4 minus 4xy plus 1. So we need our first order condition. So first we need f of x. This will be equal to 4x cubed minus 4y. And f of y equals 4y cubed minus 4x. So both of these must be equal to 0. So 4x cubed minus 4y must be equal to 0. We can factor out 4, which means that x cubed must be equal to y. In this case, 4y cubed minus 4x equal to 0. And in this case, again, factor out y, factor out 4. And now we can replace y with x cubed. So x cubed minus x is equal to 0. That means x9 minus x is equal to 0. Factor out x is equal to 0. So we can use an expansion for this function. So it's x squared minus 1, x squared plus 1, x4 plus 1 equal to 0. So now we have our options. So 1, x can be equal to 0. 2, x can be equal to 1. And 3, x can be equal to minus 1. If x is equal to 0, y is equal to 0, y is equal to 1, y is equal to 1. Now our second order conditions. So we need fxx, that is equal to 12x squared. We need fyy will be equal to 12y squared. And fxy equal to fyx will be equal to negative 4. So remember, we have 3 points, so we have 3 intervals. So we have minus, so x, we don't need the intervals with these ones. So if x is equal to 0, fxx will equal 0, fyy is equal to 0. That means fxx, fyy is equal to 0. fxy squared is minus 4 squared, that is equal to 16. So fxx, fyy is smaller than fxy squared, which means that the point 0, and did we calculate the corresponding values? I don't think we did. So the corresponding value will be 1 is a saddle point. if x is equal to 1, if xx is equal to 12, which is larger than 0, if yy is equal to 12, which is larger than 0, if xx, if yy is equal to 144, if xy is equal to minus 4, if xy squared is equal to 16. In this case, if xx, if yy is larger than f xy squared, which means, and that means the point 1 minus 1 is a minimum. And finally, if x is equal to minus 1, if xx is equal to 12, if yy is equal to 12, if xx, if yy is equal to 144, if xy squared is equal to 16, so if xx, that is larger than 0, if xx, if yy is larger than f squared xy, so the point minus 1 is a minimum. Please note that section 11.3 is not